Welcome everyone. My name is Miguel Davila. I'm an applications engineer here at GoEngineer. I am based out of the Santa Clara office here in Northern California, and I am the resident SOLIDWORKS CAD, PDM, and simulation specialist. So that's what I'm actually here to talk to you guys about today with my little presentation called Parametric Optimization versus Topology Optimization. Potato, potato, is there a difference? What is that difference? What are each of these good for? And that's what we're going to talk about today. So, for those of you who are new to GoEngineer and who are new to us, we are a SOLIDWORKS value-added reseller. We offer in-classroom training under normal circumstances, anyway, for SOLIDWORKS and all of its other products in the SOLIDWORKS family. But these days we offer a lot of online training. These are actual instructor-led courses over GoToTraining and Zoom, where we teach you anything from the essentials of SOLIDWORKS to how to use the simulation products we'll be talking about today. In addition, we have a very comprehensive suite of online resources that we've published on our website, as well as plenty of YouTube videos, of which this webinar here will actually be added onto once the recording's done. And don't forget, we offer certification vouchers as well, so you can become certified in the various SOLIDWORKS products. In addition, as customers of GoEngineer on subscription support, you are entitled to our on-demand tech support, where you can call in and ask any questions regarding SOLIDWORKS or issues that you're having. We also have SOLIDWORKS training options as well, formal training, as well as mentoring sessions that you can avail of online. And also, as we are a Stratasys reseller, we also offer 3D printing or service bureau type of work where we can print your parts as well. So those are the services that we here at GoEngineer offer to our customers. That being said, don't forget to sign up to our newsletter to get the latest on any webinars that are happening, just like this one. And don't forget to check out our website and knowledge base for any tips, tricks, and blogs on SOLIDWORKS and its many other products. And once again, don't forget to check out our YouTube channel, because that's where this webinar will be in case you miss it. Now, on to the main topic at hand. Parametric optimization versus topology optimization. These are two types of optimization studies that we can do inside of SOLIDWORKS. What are they good for, and what do they do? And if you guys have any questions during this webinar and I don't get to you, please do put them in the questions field specifically. This is something we can export, and I will follow up with you after the webinar is over. Now, before we discuss these two specific study types, let's talk more broadly about what is the point of optimization. When someone tells me they want to optimize their design, typically what that means is that they want to maximize desirable aspects of their design, such as the overall stiffness, the natural frequencies of the structure, and they want to also minimize undesirable aspects of their design, such as weight, the overall volume, or the amount of material consumed. In addition, we also just want to make our part better. There's no point in optimizing a design to make it worse, so we want to make sure that for our optimized shape, it maintains a relative improved baseline performance compared to the baseline. In addition, something else that people don't often consider with optimization is how much input they have to put in as a user. We want to be able to generate and manage these different scenarios intelligently and efficiently with the minimum user input and the minimum of solve time. And finally, once we get our optimized results, we want to be able to analyze them and identify trends so that we can take that knowledge and move forward with future revisions and iterations that incorporate the trends of where is material most important, where is a given feature most valuable, compared to other sections and other areas of our model. Now, what are the tools in SOLIDWORKS simulation that allow us to accomplish this goal? I'm going to go on a slight little tangent here and talk about design studies. Design studies are a tool that is already available in SOLIDWORKS CAD, just regular SOLIDWORKS CAD, and it is actually compatible with all levels of the simulation product suite, be it simulation standard, professional, or premium. It's important that we talk about the features of this because of how it wraps into parametric optimization. This specifically, a parametric optimization study, is available in SOLIDWORKS Simulation Professional and Premium. So you don't get this with SOLIDWORKS Premium or Simulation Standard, even though those tools do have simulation tools in them. And finally, we have topology optimization studies. Just like parametric optimization, this type of study is available in SOLIDWORKS Simulation Professional and Premium. Now, let's begin talking about these tools in depth. To give a brief overview of design studies, its capabilities are as follows. It has the ability to generate and automatically run multiple scenarios of our model geometry, our feature size, or variations in our simulation setup, maybe different loads, different fixtures, different initial displacements. It has the ability to automatically generate these scenarios and run them for us. This makes it extremely versatile. If it is a user-based input in your SOLIDWORKS model or simulation study, likely it is something that the design study can actually drive and use and vary. We also have design studies take advantage of a feature known as sensors within SOLIDWORKS. It's a little known feature that allows us to actually gather and monitor various simulation outputs and model outputs as well, and is useful to act as a threshold or a pass-fail check for our results. And finally, this is the most important thing to know about design studies. They do not exist in a vacuum. A design study is not in and of itself a study. It is an engine. It is an engine that uses other regular, normal simulations as a backend. And it requires them in order to actually give you results. All it does is really take the place of someone like me, a user, plugging and chugging in values. Now, what are the limitations of a design study? This is going to be important for later. The limitations are as follows. It is highly dependent on existing model features and dimensions. If it is not something that the user can explicitly plug and chug a value into themselves, then it is not something the design study can do. It cannot generate new cuts or extrudes or features for you on the fly. It also cannot choose values that cause rebuild errors. I'm sure every one of us has put in a fillet on a feature that is too large for the surrounding geometry, causes a rebuild error, and our part goes very red and very angry. So we cannot choose values that cause any instabilities within our model, our assembly, or our simulation study itself. We're also limited to discrete values. So while I can say I want this study to try values for this length of 5 to 50 in increments of 5, like 5, 10, 15, 20, it cannot choose some value in between those discrete increments, such as 5.637. Can't do that. And finally, because it runs on regular simulation studies in the back end, solve times are largely dependent on your input studies. So if you are running multiple iterations of a linear static study that takes half an hour to solve, well, a design study is not going to drastically reduce that like a miracle. It's still going to take however long it takes. Now, talking about specific features of a design study, we have a concept called variables. Think of these as your independent variables in a study, things that you can change. These are user-defined ranges for model geometry that it will then generate scenarios to iterate through, different combinations of these values to try out. We also have the concept of sensors and constraints. These are, once again, features in SOLIDWORKS that allow us to monitor the various outputs of our simulations. We can set it to look at things such as max stress, max displacement, and natural frequencies, and so on. And We can also specify them at a given value to act effectively as a threshold, maybe a pass-fail for our various results. Obviously, we don't want to optimize to make our design worse or behave more poorly in certain contexts, so we can automatically reject or identify and reject anything that performs worse as a result of the changes that we've made. Now, with the basics of a design study in mind, let's go ahead and talk about parametric optimization. And for those of you that have already had some experience with parametric optimization studies, spoiler alert, let's talk about our capabilities. It's actually built on a design study. It adds on top of what we already know and what we already do with a design study, with a few additional but very crucial features. So anything that a design study can do, a parametric optimization study can do as well. So it can manipulate any existing model feature or dimension or study feature. But what it adds is the range parameter type. This actually allows us, or allows the study, I should say, to choose non-discrete values. So remember the example I gave earlier, where we could, in a design study, increment 5, 10, 15, 20 in discrete steps. Well, the optimization study is unique in that it can now choose optimized values between those steps. So now it can choose that 5.635 or something, if it finds that that is the optimal value. So it's not limited to a given step size. In addition, sensors are once again coming into play, not just as constraints or things that we want to look at and observe about the various scenarios we're running, but now it's also a goal for optimization. Now we can say that we want to minimize mass. We're going to have a sensor to detect the mass of each iteration, and it's going to use that as a goal or as a point of comparison to decide which scenario is better than the others. In terms of limitations, once again, because it's built on the back of a design study, it inherits all the limitations of a design study, namely that it cannot create new features for you. It can't create new sketches or dimensions or parameters. It can only work with what's explicitly been modeled in the part already. In addition, we technically have a limit of 20 design variables, though realistically, I will say, I rarely encounter anyone who's gone that far. Normally it's really just 4 to 5 of the most important ones, for solution time's sake. And once again, a parametric optimization study does not exist in a vacuum. It is still highly dependent on the input studies that you feed it, on solve time as well as overall resolution of the results. Now, talking about the new features that it introduces, range and goals. A range establishes a minimum and maximum threshold of values for it to iterate through. So, where we might typically indicate a step size, we can now just indicate the minimum and maximum thresholds that it's going to try. We still have constraints, and once again, these act as monitors or watchdogs and tell us what a value is evaluating to in a given scenario. But we now have the ability to have them act more like thresholds and automatically throw out any results that are past or above a certain value that we want. For example, if due to the changes that we make in making a part skinnier and take up less mass, the max stress is for the same fixtures and loads exceeds yield, well, obviously we want to throw that result out, and we can do so using constraints. And finally, we have the concept of goals. This is once again a sensor that acts as a criteria for success and as a method of comparison between different scenarios that we're running to figure out what is the best one. In terms of results, what do we get out of our parametric optimization at the end of the day? What can we actually see? What can we analyze? We have what's known as the table view. This table view illustrates all the different scenarios for geometry that it tried, as well as gives the optimal one. And all of these different iterations or scenarios, These are actually full study results. They are full in the sense that I can click on them and activate them, much like configurations of a part or an assembly, and I get the full simulation results loaded, as if I had used these values from the very start and hit run myself on my individual input studies. So I have the full resolution of those results, and I'm able to create all the varying plots, cutouts, section views that I want, as if I had done a regular normal study from the very beginning. Now, let's talk about topology optimization. How is it different from a parametric optimization? What are the benefits and what are the limitations? In terms of its capabilities, unlike a parametric optimization, because of the nature of a topology optimization, in that when it reduces our model into a mesh, it will run a simulation on that structure and see which elements, which sections of material are more important than others in terms of the overall structural properties of our model, and it will go ahead and remove it element by element. It's not limited to existing features and dimensions that the user modeled themselves as it modifies and manipulates the overall shape of the model. In terms of parameters we can actually aim for, we can optimize for things such as mass, stiffness, alongside constraints, just like we did in parametric optimization for properties and thresholds like stress, displacement, and frequency. In terms of controls, how do we control it? Because remember, we're not playing around with user-defined features anymore. Very often, a topology optimization will result in a non-parametric shape, which can be difficult to manufacture with traditional subtractive manufacturing methods. We have now geometry controls that allow for greater manufacturability by affecting the strategy of how material is removed, so we have a much more realistic and manufacturable part at the end. We'll talk about that in just a bit. And what do we get as the output? We can get that non-parametric shape exported as a smooth mesh body or a mesh file, or as a solid body. And if you don't want to use that smoothed non-parametric shape directly, you can simply overlay it onto your model to act as a visual guide for additional parametric feature creation. But that all sounds great. But what about the limitations of topology optimization? What is it not able to do, or how is it limited? In terms of the limitations, we can only work on parts. Currently, the topology optimization can only be run on single parts only. If you're analyzing an assembly, you will be asked to choose an individual part of that assembly. In addition, unlike parametric optimization, we're only limited to linear statics for this topology optimization. We can't do anything that involves dynamic loading or nonlinear materials. Linear static only. In addition, the way topology optimization works is that it removes mass from an existing shape. In return, it cannot add material to our design. It cannot add material where there was none. It can only take. It does not give. And finally, this is something that sets it uniquely apart from parametric optimization. The solve time and the resulting optimized shape, or the resolution of it, is typically dependent on your mesh size, not necessarily any input studies. A topology optimization study stands on its own. It doesn't require any input studies like a parametric optimization does. In terms of the setup, because it's essentially a linear static study at its heart, it uses the same types of fixtures, loads, and mesh settings as a regular linear static study. We define goals in very similarly to a parametric optimization. We can specify that we want to minimize mass, get a best stiffness to weight ratio, for example. And in terms of constraints, we can also specify that whatever the performance of the resulting optimized shape is, we can make sure that the max displacement and stress do not exceed or are below given thresholds. Remember, we are making the part structurally less stiff by removing material. We don't want to remove so much material that the resulting structural properties fail for any reason. Now, on to the geometry controls, something completely unique to topology optimization. We have controls for symmetry. Very often we want to design a very symmetric looking part, and as we remove material from one side, we might want to make sure that a similar amount of material is removed from the other side as well. In addition, in order to make a part more manufacturable, we have demold directions. For example, as it removes material, we want to make sure that it doesn't remove material from, for example, the inside of the model itself. It's really hard to manufacture hollow internal cavities, as it turns out, using traditional manufacturing methods. We can also specify what are known as preserved regions. As it removes material from our part, we can specify a minimum amount of material it will leave in certain areas of the part. That way we have enough material there, for example, for other features that we might want to machine in later, such as threads. And finally, we have minimum thickness conditions as well that we can assign so that whatever structures it does create, it doesn't make anything too small or too thin. In terms of the results, what do we get out of a topology optimization that sets it apart? We have something called the material mass plot. Think of this as a heat map of where material is the most important for the structural performance of the part that we're looking for. And we can actually affect this and see how much material we want to keep and how much material we want to toss. And once we've decided on what we want to keep and how much, we can then smooth it, similar to remeshing functionality that we see in a lot of mesh-based manipulation tools like Blender and so on. And we can then export this as a solid or mesh body for use in additive manufacturing. Additionally, if you are limited by your types of manufacturing method, maybe you're going just plain old subtractive in the traditional sense, we do have something called the simulation result overlay. What this does is that it can graphically overlay the optimized shape on top of the existing model, so that it acts as a visual guide as you make more traditional parametric features. That way you can still take advantage of the different areas and shapes that it was able to generate for you, but this time you can use regular SOLIDWORKS sketches, dimensions, and features to actually remove that material and get a much more manufacturable, much more parametric shape at the end result. Now, the part that we've been looking at this entire time is a very simple linkage for a bicycle that I shamelessly stole from our regular simulation class. And we're actually going to do a side-by-side comparison of these two types of studies and what they were able to generate for us. But before we do that, let's set aside some ground rules. For the material, we are using a 1060 aluminum alloy. For the loads, we have a simple 800 Newton force on one of these cylindrical faces where it's attached to a shock. And for the fixtures, we are emulating how this individual linkage part is attached to the rest of the bicycle frame and other components using fixed hinges and remote loads. So these are things that are completely normal to any linear static study. And as for the mesh size, we're going very coarse here because I didn't want to wait a very long time for these studies to solve. So we're going with this element size, which is very coarse for the size of the part itself. And for our baseline results, running all of these settings as a super basic linear static study, I saw max stress of 5.46 megapascals, a max displacement of 0.0035 millimeters, and an initial starting mass of 342 grams. This is our baseline. Now, to optimize this part, these are our goals. We want to minimize the mass, obviously. We also want to maximize, or we want to limit the max displacement. As we are lightening the overall part, that will naturally lend it to being less stiff as a whole. As a result, we can expect the max displacement and resulting stresses that we see for the same types of loads and fixtures and material to rise. And we want to make sure that for whatever results that we're getting, it does not rise beyond 1.3 times the baseline. In addition, we want to make sure our max stress is less than that we could possibly see in our optimized shape is less than 90% of the material yield strength, so about 25 megapascals. Now, let's talk about the results, or my apologies, allow me to quickly switch over to SOLIDWORKS to show you how this is done. Here I have my basic part right here. It's nice and big and chunky, and I have a feeling it's using up more material than is strictly necessary. As you can see, I've already run a basic linear static study on this part, so I have a good idea of how it currently performs. Now, to make a new design study, all you have to do is right-click on one of your study tabs down here and hit Create New Design Study. In order to turn this into a parametric optimization and not just a regular design study, make sure to check the Optimization button right here. This will turn it into an parametric optimization study. Now we need to set up our variables, constraints, and goals. For our variables right here, we're going to add parameters. This is going to be very similar to how we add parameters, how we add equations and variables inside of a SOLIDWORKS model. I go ahead, use this drop-down, select Add Parameter, and I can click and attach any one of the visible dimensions or any one of the dimensions in my model, like so. First, I'll create the variable name. I'll call this top cutout, and it will correspond to the length of this rectangular cutout here at the top, this 12.7. I'll simply highlight it and click on it, and it will attach it like so. You can see how it's linked just like this. Now I'll do the bottom cutout right here, and I'll go ahead and select this 40 millimeter dimension, which governs this rectangular cutout that we see at the bottom. I'll hit apply to start a new row. I'll make one for the overall width of the part, and I'll link it to this 50 millimeter feature right here. Now, I have a feeling that if I bulk up the part in the width, I might be able to get away with increasing the size of these two cutouts at the top and bottom. So that'll play into my parameters later. I have a similar feeling about this 25 millimeter dimension right up here, which governs the thickness of this profile in this direction. So I'm going to vary that by highlighting it, clicking on it like so, and labeling it thickness. And once I'm done, I'll hit apply, and I'll hit OK, and now I can assign my variables through the drop-down window right here. And let's see. Now, in order to take advantage of the capabilities of the optimization study, I'm going to switch them over to the range type of parameter, where I can specify the minimum and maximum range. As I mentioned, I definitely want the cutouts to only get bigger from here. So for the top cutout with its base value of 12.7, I have a feeling that I want this to be able to grow up to a maximum of 60, for example. For this bottom cutout, it starts out at a length of 40, so I'll go ahead and plug that in. I only ever want it to grow bigger, and I have a feeling that it can max out at 55. If you guys are wondering where I'm pulling out these numbers from, that's because I practiced this before the webinar, and past these values, the features will actually fail and cut clean through the part. So remember, we can't choose values that don't make sense and cause rebuild errors. As for the thickness here, I'm going to say I can only get it to be, I definitely want it to grow smaller than 25.4, but I have a feeling that if I make this a bit chunkier and larger, I might be able to get away with cutting away more in the middle. So I'm going to say a minimum value of 20. It can grow smaller by 5 millimeters, but it can also grow in size by, according to this post-it I have taped to my monitor, 35 millimeters. Now for the width, I'm going to say that I want it to grow smaller as well, ideally, but I want to leave the possibility open for growing it in case that means I can cut out more in the middle. So I'm going to leave it to a minimum of 35 millimeters and a maximum of 75. Now to apply my constraints. I'll go ahead and use the drop down once more. I'll hit Add Sensor right here, and this allows me to create that SOLIDWORKS feature known as a sensor. To take advantage of simulation, simply under the sensor type select Simulation Data, and under the data quantity, choose the type of input, or output I should say, that you want to monitor. I'll choose Max von Mises stress, and I'll choose megapascals, and I'll set it to look up the maximum across the entire model. There we go, that's my sensor. I'll go ahead and do another one real quick before we modify that. I'll do one this time for max displacement. Once again, selecting simulation data, the data quantity type is displacement, and I want to use resultant displacement now, and in the units of millimeters, and I'll set it to use the maximum across the entire study. Now, what's very important here is that we look at the logic. Remember, these are pass and fail constraints. We want to make sure that we reject any stress such that the maximum that we can experience, or the stress that we want, is less than the maximum of 24.81 megapascals, and our displacement is no greater than or is less than the maximum of 0.0045 for all of our results. This will make it so that anything that exceeds these values will automatically be rejected. Now, if you have multiple input studies, please make sure to select the appropriate study name here for a given constraint, because it will actually look at that value for that given input study. Now for our goals, once again, we're going to use a sensor. I'm going to go ahead and hit Add Sensor over here and just add a general one that looks at mass. And we want to go ahead and select Minimize right here. We want to minimize the overall mass as much as possible. And now it will go ahead and, if I hit Run, it will go ahead and generate a variety of scenarios to try and go ahead and gather the maximum stress, displacement, and mass of these various runs of these values. And it's going to compare them and present me with the optimal value. I'm not going to run it right now because very often with optimization studies, what we save in picks and clicks and automation, we make up for in the time it takes to run, however many scenarios it comes up with. So we're not going to do that for the sake of time. Now, how do we make a brand new topology study? It is a study all on its own, so I can just hit New Study. It is a different type of study. So here, under Design Insight, I'll just go ahead and select Topology Study, like so. Now, remember, a topology study is, at its core, a linear static simulation. So I'm going to cheat a little bit for the sake of time and simply copy over my existing materials, fixtures, and loads over to my topology study like so. Here's a little pro tip for everyone. You can copy settings between studies by simply left-clicking and dragging from the simulation feature tree and dropping it into the study tab name down here below. So I'm quickly going to copy my fixtures, loads, and mesh, just so that we can save time. Awesome. And now you can see in my topology optimization, I now have these set up, ready to go. Now let's focus on features unique to a topology optimization. Here under Goals and Constraints, I can say I want to minimize mass, and I can now also specify what I want to act as a constraint. I want to make sure, once again, just like with my parametric optimization, that my max displacement is not 1.3 times my initial baseline, or what I have in front of me right now, and my stress and factor of safety does not exceed 90% of the material yield strength, or you can explicitly just call out a value that you want to use. As for manufacturing controls, you can simply right-click on the manufacturing controls node right here. We can start by adding some preserved regions. Maybe for these cylindrical faces right here, I want a minimum amount of material so I can actually put in threads and pins and all that jazz. I can specify a preserved depth like so, and it will actually offset around those faces to act effectively as keep-out zones for the algorithm, where the algorithm decides to remove material. Additionally, I can go ahead and specify thick symmetry planes as well, so that I still have a very symmetric part at the end. Simply select your planes of symmetry and the type of symmetry that you want. And the same goes for demold directions. You can specify an edge or a plane to act as the demold direction. And I'm going to, for example, make it so that I have two molds coming across this direction across the thickness. And I'm going to specify a mid-plane demolding control there. That way it doesn't take away part material in such a way that it generates an overhang. And that's it. I'm ready to run this topology optimization. You'll notice that it took considerably less time on the input, and that's what will factor into our analysis of which is best in just a moment. Let's go back to the presentation and discuss the results. Behold, the optimized shapes. As you can see, my parametric optimization is quite a bit skinnier, but it's not quite as drastic as the topology optimization. In terms of our results, we can see that both of these were able to reduce the mass, but the topology optimization even more so than the parametric, because it wasn't restricted by any existing features. In terms of the max stress, we still got very comparable results, but because the mass reduction was so great in topology optimization, the max stress did in fact rise as expected. As for displacement, we still got very comparable displacement results across the board, but the key thing here is solution time. My original study took just under 2 minutes for a single linear static analysis. My parametric optimization with 30 different scenarios took around 10 to 15 minutes really. But the topology optimization, for its very drastic results, it took approximately 40 minutes for a single run. So that was way more time that it took to actually get this result compared to the other methods. So what have we learned from this? Parametric optimization is great for anything where the output is expected to be very prismatic with discrete dimensions and very normal manufacturable shapes. Also, it's your only option if you want to do anything or analyze a scenario beyond linear statics on single individual parts. And finally, it's really great for use when the features that you want to optimize for already exist as model features in your parts and assemblies. Topology optimization is great for very complex non-parametric shapes that really lend to recent advancements in additive manufacturing. It's great for drastic changes to model geometry that are independent of the actual features that the user has modeled themselves. And finally, it's great for optimization on single parts in a linear static context. Beyond that, you can't use topology optimization. Now, for tips and best practices, here's what I recommend for you guys. Number 1, run your initial studies first. If it can't run even once, optimization won't run at all. So do a quick sanity check, make sure you've actually set everything up correctly, and run it at least once. In addition, because of the similarities and the requirements of an input study for parametric and the linear static requirement of a topology optimization, you can simply copy and paste study features anyway to save time. So it's not like you're doing anything you won't use. If you're using parametric optimization, start with the 3 to 4 most significant parameters first, and when specifying your ranges, don't purposefully undershoot when you know that that's not going to trend toward the results you want. Only use values that you actually think will yield good results. And finally, if you're using topology optimization, don't start with a skinny model, start with something big and chunky. Remember, it can't add material, so by starting with something big and chunky and overbuilt, you give it more avenues and more space to play around in. And finally, you can use it to take advantage of additive manufacturing and the relative ease with which additive technologies can generate complex geometry compared to traditional manufacturing methods. And that is my presentation. Those are some tips and tricks and some general thoughts on what makes parametric versus topology optimization different and what each of the studies is good for. If you guys have any questions, feel free to contact me. Feel free to drop some questions in the chat, and I will get back to you as soon as I can. Yes. And that is the end of our little webinar here. Yeah, I'll stick around for a bit in case anyone has any questions, so feel free to ask away. Excellent question. Got a question here. How do we impose the optimized shape over the original part? Well, let me go ahead and pull up SOLIDWORKS, and I actually ran the topology optimization study in advance for scenarios just like this. We actually, first off, make sure that your topology optimization is actually run. It needs to have been run first and foremost. Then you go back to your model tab where you can now model your part. And it's right here under the view settings in the heads-up display, where we would typically turn on things like real view graphics, shadows, and so on. We now have a special option when we have simulation studies called simulation display. And this works such that for any plot that you have, be it a regular simulation study or topology optimization, we can select and highlight it like so, and have it be overlaid onto our model, sort of like a filter. This is a full 3D view, and all of our features are still accessible, so I can now simply just make my sketches and cutouts just like I normally would, just tracing it like so. So yes, excellent question. So yeah, once again, this simulation overlay is found here on the model tab. Here under view settings, just make sure to hit simulation display. I will add, you must have simulation on. So if you don't have the add-in on, you won't actually see the simulation display options right here. And also you have to have the studies run in order to look at the plots. Oh, absolutely. This presentation in its entirety is being recorded, and it will be on our YouTube channel, where we have a ton of other great webinars for you guys to check out. So yes, we will be sending out the webinar link for the recording, but you can also watch it on demand on YouTube. Another question here. With pulling the geometry in the sketch, is there a way to make it symmetrical to accommodate both sides? Yes. So, for example, this is just regular sketch modeling at this point. Remember, the simulation overlay is honestly nothing more than a very pretty graphic that is still very useful. So, for example, I'll go ahead and create a quick center line right here, just like... Whoops, accidentally kicked myself out of the sketch. My bad. Let me go ahead and make a quick center line here. And for example, if I'm working with a spline, I would still, just like with a regular sketch, draw half of it, like so, and make it go up to the center line. Let me go ahead and add some spline constraints right here, so at the very least it's nice and tangent. Go ahead and manipulate things so it looks nice and pretty. There we go. And I'll simply use the mirror entities command, just like I normally would inside of a sketch. So once you have applied the simulation overlay, it's a simple matter of your regular SOLIDWORKS sketching and modeling skills at this point. So now I have a very symmetric profile. And I can go ahead and, let me just close off this shape. And I can go ahead and do a regular extruded cut from here. Similarly, for any cutouts that I do on one side, I'll just use the regular SOLIDWORKS mirror feature for those features in order to make everything nice and symmetrical in my cutouts. Yes, excellent question. Yes, you can absolutely export a mass or a material mass plot. You simply go to the mass plot itself. Let me go to my completed study right here. You simply go here under Results, right-click on your mass plot, hit Show. Let's see, did I... let me quickly reload my model. So, let's see, reload. Let me quickly reload my model so that I can actually show you the plots. Yes, we just, with regards to the other question on symmetry, yes, it's just a matter of tweaking the spline. As I mentioned, it's just a matter of regular SOLIDWORKS modeling practices at that point. So, let me go ahead and show my material mass plot. And once I show my material mass plot here, or sorry, I can now, once it's shown, I can now right-click on it again and hit Export Smooth Mesh. This will now allow me to export the smooth mesh as a separate file or a separate configuration, and I have the option to do it as a graphics body, as a solid body, or a surface body. So for example, if I want to do it as a solid body, I can then hit check. It will then spit it out as a new file, and this file I could then feed into anything that takes in SOLIDWORKS files, for example, or I can then subsequently export it into an STL using the normal save as functionality. So for example here, I have the mesh. I actually chose it as as within this configuration itself. So now you can see I do have a mesh body. Using whatever method, once you actually have this, you simply do a save as. And I'll go ahead and do a save as an STL, like so. And now it will become a STL, which is the typical standard format for a lot of 3D printing software these days. Many also, in particular the ones with Stratasys, they can GrabCAD Print can take in just raw SOLIDWORKS files, so you may not even have to do this additional save as step. But that is the normal MO for this. So yeah, just to show it off, since it looks like we have the time, I used this slicer for my own personal 3D printer, and I spat this out as an STL. And I can now go ahead and load this in. So yes, now I can actually go ahead and browse for that STL file like normal. Load this into your slicer, and it's ready to print. Or you slice it, and then it would typically be ready to print with the G code that is generated. Alright, it looks like we don't have any more questions, so well, thank you everyone. Thank you for attending. Thank you for participating and asking some good questions here for everyone. I'll go ahead and end this recording shortly, and we'll go ahead and send out the link once everything's done processing. And don't forget, you can check out this webinar and many others on our YouTube channel. So, as they say these days, like, comment, and subscribe, I guess. So yeah, thank you everyone. My name's been Miguel Davila, Applications Engineer here at GoEngineer. Thanks again very much for being part of this webinar.